In the boundless reaches of the cosmos, where stars burn bright and galaxies swirl in endless dance, there are places so strange, so incomprehensibly vast, that they challenge everything we thought we knew about the universe. One such enigma is the KBC Void, a cosmic anomaly so immense it stretches across nearly 2 billion light-years, a region of emptiness so profound it distorts the very fabric of reality itself. Imagine, for a moment, standing at the edge of this void, looking out into a chasm of space where stars and galaxies fade into a void that seems to consume them. This is not just a strange cosmic feature, it's a force that fundamentally alters our understanding of the universe. This massive emptiness, nestled at the heart of the cosmos, is home to our very own Milky Way galaxy. Yes, Earth, the cradle of human civilization, resides within this void, in a region of space that should not exist according to the laws of physics. But it does, and that fact has shaken the foundations of modern cosmology. The KBC Void is not just empty space, it's a place where the very laws of nature appear to bend, a place where gravity, matter, and even the expansion of the universe itself behave in ways that defy expectation. What we once thought was the uniform, predictable stretch of space has turned out to be a deceptive illusion. The KBC Void plays a role so critical, so extraordinary, that its discovery has forced scientists to rethink the way we measure and interpret the vast universe around us. The void is altering the very rate at which the universe appears to expand. It is as if we are standing at the center of a cosmic illusion, one that has shaped our observations, warped our measurements, and left us questioning what we know about the fundamental workings of the cosmos. But why does it matter? Why should we care about a void, a place where galaxies are scarce and the light seems to dim? Because this emptiness is not just a passive feature of space, it is actively influencing our perception of the universe. It is forcing us to confront a profound question. What does it mean to be located in such a unique, rarefied space? And more importantly, how does it change our understanding of cosmic expansion? This is the beginning of a journey through the void, a journey that will take us deeper into the heart of space itself, where the very nature of the universe is being rewritten, one discovery at a time. As we venture through the layers of cosmic emptiness, we will uncover not only the void's mysterious impact on our measurements, but also the unsettling truth about our place in the grand, expansive universe. Prepare to see the universe differently. We begin with the discovery that shattered cosmology itself. For centuries, scientists have meticulously measured the universe, striving to understand its rate of expansion, its origins, and its vast, intricate structure. Yet, despite their best efforts, one mystery has stubbornly persisted, one that has left even the brightest minds scratching their heads in confusion. This enigma is known as the Hubble Tension, a glaring discrepancy in the measurement of the universe's expansion rate. Imagine this. Two separate methods, both incredibly precise, should give us the same answer. Yet they don't. One method, which measures the ancient cosmic microwave background, CMB, the faint radiation left behind from the Big Bang, gives us a universe expanding at 67 kilometers per second per megaparsec. The other, which measures distant supernovae in the nearby universe, suggests a faster expansion rate, about 73 kilometers per second per megaparsec. That's a 9% difference, a number that, at first glance, may seem small. But in the precise world of cosmology, this difference is enough to cause a crisis. For years, cosmologists have debated and speculated about this discrepancy, trying to reconcile the numbers. Some have pointed to potential errors in our measurements, while others have proposed adjustments to our understanding of dark energy or gravity. Yet, no solution has fully resolved the puzzle. But what if the key to solving the Hubble tension lies not in new physics, but in the very place where we happen to live? Enter the KBC Void. This cosmic desert, stretching across nearly 2 billion light-years, has become the unlikely focal point of this ongoing mystery. At first, the discovery of this vast emptiness seemed like an odd curiosity, a feature of the universe that we could study but might never fully understand. However, as scientists delved deeper into its implications, they realized something profound. The low density of the KBC Void, its lack of matter, may be responsible for the discrepancy in expansion rates. In the standard model of cosmology, the universe is thought to be relatively uniform at large scales. Matter is scattered across space in a way that should result in a predictable, smooth expansion. But the KBC Void isn't just empty. It's vast and underdense, containing only 80% of the matter that should be there. This emptiness isn't just an absence of galaxies, it's a cosmic anomaly that bends the very rules we've used to measure space and time. The implications of this discovery are nothing short of revolutionary. The KBC Void, it turns out, isn't merely a quiet corner of the cosmos, it is an active player in the grand scheme of cosmic phenomena. The low density of the void could be warping our measurements of cosmic expansion. Gravitational forces in the region behave differently, and the movement of galaxies within the void is affected by its vast emptiness, making them appear to move faster than expected. This, in turn, inflates the local expansion rate, explaining the 9% discrepancy between the two methods used to measure the universe's growth. This realization doesn't just challenge our current understanding, it has the potential to reshape the fundamental laws of physics as we know them. If the KBC Void's influence on the Hubble tension is confirmed, it will force us to rethink how we measure space, time, and gravity. More importantly, it could open new pathways for exploration, offering fresh insights into the universe's most profound mysteries. What's at stake here is more than just a scientific puzzle. It's our understanding of the universe itself. The KBC Void is forcing us to confront the possibility that our measurements and assumptions about cosmic phenomena may be fundamentally biased by our position in the cosmos. Are we truly measuring the expansion rate of the universe, or are we simply measuring it from within a cosmic whole that distorts our perception? The discovery of the KBC Void could change how we approach cosmology, shifting the focus away from traditional models and opening up entirely new avenues of research. It's a cosmic riddle that demands answers, one that may reveal deeper truths about the nature of the universe and our place within it. As we begin to understand the role of the KBC Void, we may find ourselves at the precipice of a new era in our exploration of the cosmos, one where the boundaries of knowledge are pushed farther than ever before. To understand the significance of the KBC Void and its potential connection to the Hubble tension, we must first journey back in time, to a pivotal moment in the early 20th century when one of the most groundbreaking discoveries in cosmology was made. It was 1929 when Edwin Hubble, working with a young team of astronomers, revealed something that would forever change the way humanity viewed the universe. The cosmos was expanding. Hubble's discovery wasn't just a confirmation of what some had speculated, it was a revelation. By measuring the redshift of galaxies, Hubble showed that galaxies are receding from us, and the farther away they are, the faster they move. This was the first direct evidence of cosmic expansion, and it fundamentally altered the trajectory of astronomy and cosmology. In essence, Hubble showed us that the universe is not static, but is instead stretching, growing ever larger as time marches forward. This discovery laid the foundation for our current understanding of the universe, setting in motion a series of questions and theories that would span the next century. As the years passed and technology improved, scientists began to measure the rate of expansion of the universe with increasing precision. In 1998, a groundbreaking discovery further expanded our knowledge when astronomers observed distant supernovae and concluded that not only was the universe expanding, but the expansion was accelerating. This acceleration, driven by a mysterious force dubbed dark energy, has since become one of the central puzzles of modern cosmology. Yet, despite these monumental strides in our understanding of the universe's behavior, a persistent problem has remained: the Hubble tension. In recent decades, cosmologists have discovered a significant discrepancy in the measurements of the universe's expansion rate, an issue that has only deepened with time. The Hubble tension refers to the gap between two sets of measurements of the Hubble constant, the number that defines how fast the universe is expanding. On one hand, the cosmic microwave background, CMB, gives us one value based on observations of the universe when it was just 380,000 years old. This ancient light suggests that the universe is expanding at about 67 kilometers per second per megaparsec. On the other hand, measurements from more recent local observations, like those from supernovae, suggest a faster rate of expansion, around 73 kilometers per second per megaparsec. This 9% difference is not just a small deviation, it represents a major gap in our understanding of the universe's behavior. Initially, scientists believed that the discrepancy might be due to measurement errors. Perhaps the methods used to determine the rate of expansion were flawed in some way. Maybe there was a problem with the calibration of instruments, or an overlooked source of uncertainty was affecting the results. For years, astronomers and physicists tested different hypotheses, attempting to resolve the tension. Some suggested that the tools and techniques used to measure the expansion rate in the local universe were unreliable, while others speculated that dark energy might not be the constant force we thought it was. However, the discovery of the KBC Void has brought new light to the problem. What if the solution to the Hubble tension doesn't lie in the methods we use to measure expansion, but instead in the very location from which we are measuring it? The KBC Void, with its massive emptiness and underdensity, could be the key to understanding why our measurements of cosmic expansion differ so widely. The void is not just a passive feature of space, It's a dynamic force that could be influencing the way we measure the rate of expansion in our local universe. We live within this void, and its unique properties may be distorting our measurements, making the universe appear to expand faster locally than it does globally. The Hubble tension, long a source of frustration for scientists, might be a direct consequence of our position within this enormous cosmic bubble. The low density of the KBC void affects everything from the gravitational pull of galaxies to the movement of light itself. Within this bubble, the usual rules of cosmology seem to bend and twist in ways that we hadn't anticipated. In a sense, the KBC void is not just a discovery, it is a game changer. It forces us to rethink the assumptions that have guided cosmology for decades. Perhaps our position within this massive underdense region is the reason we've been measuring the universe's expansion from a skewed perspective all along. The solution to the Hubble tension might not involve new physics or new measurements, but rather a new understanding of our own unique place within the cosmos. As we move forward in our exploration of the universe, this discovery compels us to ask new questions. What does it mean to live in such an extraordinary location? And what other unknowns might be lurking in the vastness of space, waiting to challenge our understanding of the universe even further? The KBC void has opened a door to a deeper understanding of the cosmos, one that will continue to shape our journey into the unknown. To truly grasp the significance of the Hubble tension and its potential connection to the KBC void, we must first delve into the fundamental scientific principles that underpin our understanding of the universe's expansion. The universe, as we know it, is constantly stretching, with galaxies moving away from each other at speeds proportional to their distance. This expansion is governed by a fundamental principle known as Hubble's law, named after Edwin Hubble, who first observed this relationship in 1929. The law states that the farther a galaxy is from us, the faster it appears to be receding, a direct consequence of the stretching of space itself. The key to understanding the Hubble tension lies in the two primary methods used to measure the rate of this expansion, known as the Hubble constant. The first method, the one that measures distant galaxies, relies on observing objects that are far away, sometimes billions of light years from Earth. By studying the light emitted from distant supernovae or galaxy clusters, scientists can calculate the rate at which these objects are moving away from us. This method provides a relatively straightforward measurement of how fast the universe is expanding in our local neighborhood. The second method involves studying the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang that fills the entire universe. The CMB represents the state of the universe when it was just 380,000 years old. By studying the fluctuations in this radiation, scientists can model the early universe and calculate the expansion rate at that time. This provides us with a snapshot of the universe at its infancy, offering a measure of the universe's expansion from a much earlier point in cosmic history. However, the problem arises when the results from these two methods don't match. Measurements of the Hubble constant using the CMB data suggest that the expansion rate is about 67 kilometers per second per megaparsec, whereas measurements from distant galaxies suggest a faster expansion at 73 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, has left scientists puzzled for years. Both methods are incredibly precise, so the question is, why are the results so different? This is where the KBC void comes into play. The KBC void, a massive region of space with significantly lower matter density than the rest of the universe, could be the key to resolving the puzzle. In areas of space like the KBC void, the usual gravitational dynamics that govern the expansion of the universe are altered. In more typical regions of the universe, gravity acts as a counterforce to dark energy, the mysterious force responsible for accelerating the expansion of the cosmos. Gravity, in these denser regions, works to slow the expansion of space, helping balance the effects of dark energy. But in the KBC void, the story is different. The low density of matter within the void means that gravity is weaker, unable to exert the same pull that it does in denser regions of space. As a result, dark energy's influence is far more pronounced in the void. Without gravity counteracting it, the void expands at a faster rate than the rest of the universe. The gravitational forces that would normally slow the expansion in denser regions are diminished here, causing the expansion of space within the void to accelerate. This accelerated expansion in the KBC void could explain the discrepancy between the two methods of measuring the Hubble constant. The measurements taken from the nearby galaxies are influenced by the gravitational imbalances created by the void's low density. In this region of space, the galaxies are being pulled outward at a faster rate, making the universe appear to expand faster than it actually does in other parts of the cosmos. Essentially, we're measuring the universe's expansion from within a bubble, where the gravitational forces are skewed by the void's unique properties. On the other hand, the cosmic microwave background measurements are unaffected by these local gravitational influences. The CMB offers a snapshot of the universe's expansion at a much earlier time, when the cosmos was much more uniform and the effects of voids like the KBC Void were not yet pronounced. As a result, the CMB data reflects a more consistent global expansion rate, unaffected by the peculiarities of our local environment. This presents a compelling theory. The Hubble tension is not a problem with our measurements or methods, but rather a result of our unique position within the KBC Void. The void's lower matter density and its effect on local gravity may be inflating our local measurements of the expansion rate, while the CMB reflects a more accurate global expansion rate. If this theory is correct, it would mark a significant shift in our understanding of cosmology. The KBC Void, which was once thought to be just an odd feature of the cosmos, could be at the heart of one of the most fundamental mysteries in modern science. It would mean that our observations of the universe's expansion have been fundamentally altered by our location within a massive, underdense region of space. This realization could reshape how we measure the universe itself, potentially altering everything from our understanding of dark energy to the age of the universe. In essence, the KBC Void is not just a scientific curiosity, it's a key to unlocking one of the biggest mysteries in cosmology. As we continue to explore its implications, we may find that the void offers more than just a glimpse into the vast emptiness of space. It may hold the answers to questions that have confounded scientists for decades. And with those answers, our understanding of the cosmos could be transformed in ways we never thought possible. In the ever-expanding field of cosmology, new discoveries are constantly reshaping our understanding of the universe. In recent years, the KBC Void has become a focal point for researchers working to untangle the enigma known as the Hubble tension. The Hubble tension, which has perplexed scientists for decades, may finally have an answer, one that lies not in our methods or tools, but in our very position within the vast cosmos. Thanks to advances in technology, astronomers have been able to conduct highly detailed observations of the KBC Void, as well as run sophisticated simulations to explore its impact on cosmic measurements. Using the most powerful telescopes and computational models, researchers have begun to reveal the subtle yet profound ways in which the void's unique properties influence the measurements of the universe's expansion. One of the most groundbreaking findings from recent studies is the identification of a Hubble bubble, a local region of space shaped by the KBC Void's underdense nature that accelerates the expansion of the universe around us. This bubble effect distorts our local measurements of cosmic expansion, making it appear as though the universe is expanding at a faster rate in our immediate vicinity than in the universe as a whole. Astronomers have employed advanced telescopes, such as the James Webb Space Telescope and Vera Rubin Observatory, to gather data from distant galaxies. These observations have provided invaluable insights into how galaxies move within the KBC Void, revealing that the motion of galaxies within the void is not uniform. Instead, galaxies near the edge of the void are moving outward at speeds significantly higher than those measured in denser regions of space. This discrepancy in motion is a direct result of the gravitational imbalance caused by the void's low density. Simulations have played a crucial role in confirming these observations. By modeling the dynamics of the KBC Void and its effects on surrounding galaxies, scientists have been able to replicate the observed discrepancies in expansion rates. These simulations show that the gravitational forces within the void are weaker, allowing dark energy to dominate and drive the accelerated expansion of space. As a result, galaxies within the void appear to recede from us at a faster rate than those outside it. This creates a local Hubble constant, one that measures a faster rate of expansion than the global, more consistent value derived from the cosmic microwave background, CMB. These findings have profound implications for cosmology. The recognition of the Hubble bubble suggests that our position within the KBC Void is fundamentally altering our perception of the universe's expansion. The local expansion rate we observe is not necessarily representative of the true rate across the universe. It is biased by the gravitational effects of the void we inhabit. This means that the discrepancy between the two methods of measuring the Hubble constant, the CMB and local measurements, may not be a result of flawed data or measurements, but rather the result of our location within an unusually large and underdense region of space. What makes these discoveries so exciting is that they offer a potential resolution to the long-standing Hubble tension. If our local measurements are being influenced by the unique properties of the KBC Void, then the true expansion rate of the universe may not be as fast as our nearby observations suggest. Instead, it could align more closely with the slower rate observed in the cosmic microwave background, which reflects the universe's expansion from a time long before the void had such an impact on our measurements. The implications extend beyond just the Hubble tension. These studies are pushing the boundaries of cosmological research, offering new insights into the role of voids in the broader structure of the universe. Voids like the KBC Void are not just empty spaces. They are dynamic, gravitationally distinct regions that shape the very fabric of space-time. As astronomers continue to investigate these voids, they are uncovering new ways in which dark energy, gravity, and the large-scale structure of the universe interact. In addition to confirming the Hubble Bubble Theory, these advancements in observational technology and computational modeling are providing a clearer picture of the KBC Void's size, depth, and influence. By mapping the motion of galaxies within and around the void, scientists are refining their understanding of its structure and its impact on cosmic measurements. As more data is collected, researchers will be able to refine their models, bringing us closer to a unified theory of cosmic expansion that accounts for the unique local conditions within the KBC Void. But the discoveries don't stop there. The ongoing exploration of the KBC Void has opened up new questions about how the universe organizes itself on large scales. If the void's properties can so dramatically alter our measurements of cosmic expansion, what other unseen forces might be at play? What role do other voids in the universe play in shaping our understanding of space-time, dark energy, and gravity? As the research continues to unfold, it's becoming increasingly clear that the KBC Void is not just a passive observer in the cosmos, it is an active participant in the great dance of cosmic forces. The more we understand its role, the more we may be forced to reconsider some of the most fundamental principles of modern physics. What was once thought to be an anomalous feature of the universe could, in fact, be the key to unlocking a new era of cosmological understanding. The discovery of the KBC Void's impact on the Hubble tension has the potential to rewrite textbooks and reshape the future of cosmology. As scientists continue to observe, simulate, and analyze the void's effects, we may find ourselves on the brink of a revolution in our understanding of the universe. And with each new discovery, we inch closer to understanding our place in the cosmos, and how the vast emptiness of space can shape the very way we perceive the universe itself. The discovery of the KBC Void and its potential role in resolving the Hubble tension holds far-reaching implications for the field of cosmology. If the theories currently being explored are confirmed, this could represent a paradigm shift in our understanding of the universe, one that would reverberate across multiple scientific disciplines and fundamentally alter the way we approach space exploration. At its core, the KBC Void challenges the very foundations of how we measure cosmic phenomena. For decades, we've relied on certain assumptions: that the universe is expanding at a uniform rate, that our measurements of expansion are reliable across vast distances, and that the laws of physics hold true at every corner of the cosmos. But the discovery of the KBC Void, an immense underdense region that distorts our observations, has introduced a significant variable that throws these assumptions into question. If our position within this void has been influencing the measurements of cosmic expansion, it could mean that our understanding of the universe's growth, its age, and even its future trajectory needs to be recalibrated. One of the most immediate consequences of this discovery is that it could force a redefinition of the laws governing the universe's expansion. The Hubble constant, a key figure in cosmology, has been at the center of an ongoing debate over whether it accurately reflects the true rate of cosmic expansion. With the KBC Void influencing local measurements, cosmologists may need to reconsider the assumptions that underpin the calculations of this fundamental constant. The Hubble bubble, as researchers are calling it, could become a central concept in cosmological models, leading to revised equations and new interpretations of the forces driving cosmic growth. This, in turn, could have profound effects on the accuracy of cosmological models. Current models of the universe, including the widely accepted lambda cold dark matter (LCDM) model, rest on certain assumptions about the uniformity and behavior of cosmic expansion. If the KBC Void's influence is confirmed, these models will need to account for the variability of cosmic expansion across different regions of space. We may find that the universe is not as uniform as we once believed, that our local environment plays a more significant role in shaping our observations than we thought. This could lead to more nuanced and complex models of cosmology, one that considers local voids, gravitational anomalies, and their effects on larger-scale cosmic phenomena. The implications for deep space exploration are also significant. If the universe's expansion is being measured differently depending on location, we may need to adjust how we plan future missions to explore distant galaxies and study cosmic events. Instruments that rely on accurate measurements of distance, time, and expansion, such as those used in deep space telescopes and probes, could be affected by the same distortions we see in the KBC Void. Understanding how these local anomalies influence our measurements is crucial for ensuring the success of missions that aim to observe the farthest reaches of space. Moreover, the discovery could prompt a new era of space exploration, one that embraces the idea that our position within the universe might fundamentally shape what we see. Space agencies like NASA, ESA, and others will likely need to reassess how they plan to study distant galaxies, supernovae, and other cosmic phenomena. New instruments may be designed to account for these local variations, allowing for more accurate data and a clearer picture of the universe's true nature. This could lead to groundbreaking discoveries about the structure of the universe, the role of dark energy, and the evolution of cosmic voids. The study of distant galaxies could undergo a transformation as well. Understanding the influence of local voids like the KBC Void on cosmic measurements could lead to more accurate methods of determining distances to far-off galaxies. Currently, astronomers use various techniques, including the measurement of redshift and the brightness of distant objects, to estimate how far away galaxies are. However, these measurements are subject to the distortions of local gravitational fields, including the influence of voids. If the KBC Void's effects on expansion are confirmed, it could lead to more precise tools for gauging distances in space, reshaping our ability to map the cosmos. As we redefine our understanding of the universe, we might also need to reimagine our place within it. For centuries, humanity has sought to understand the cosmos, striving to position ourselves in the larger tapestry of space and time. But what if we are not just passive observers? What if our location inside the KBC Void, this vast, empty region of space, means that we've been looking at a skewed version of the universe all along? Our very measurements could be biased by the space we inhabit. This realization doesn't just alter our scientific approach, it also challenges our philosophical view of the universe. It reminds us that even in our quest for knowledge, we are inextricably linked to the unique environment in which we reside. Looking further ahead, the future of cosmology could see a series of breakthroughs that flow from the understanding of the KBC Void's influence. As observational technology advances, thanks to missions like the James Webb Space Telescope, which is capable of peering deeper into space than ever before, the nuances of cosmic voids will become more apparent. These voids are not just empty gaps between galaxies. They are dynamic, active players in the universe's evolution. They shape the structure of space, influence the movement of galaxies, and could provide critical insights into the behavior of dark energy. Studying these voids more thoroughly could offer a wealth of information about the forces that govern the universe's expansion and the large-scale structure of the cosmos. In the coming decades, we may see an increasing focus on mapping voids across the entire observable universe. Rather than being seen as peculiar outliers, these voids may become central to our understanding of cosmology. By examining voids in different regions of space, astronomers will be able to compare their properties and understand how they influence the overall structure of the universe. This could lead to new insights into the formation of galaxies, the behavior of dark matter, and the role of gravity in shaping cosmic evolution. Finally, the discovery of the KBC Void's effects on the Hubble tension opens up a new frontier for scientific exploration, one where the most fundamental laws of the universe are not fixed but subject to the context of space itself. In the future, we may find that the universe we observe is just one part of a much more complex cosmic landscape, where local phenomena like voids, clusters, and gravitational fields shape our understanding of reality. This realization may not only change the way we study the cosmos, but it could also challenge our long-held beliefs about the uniformity of space and time. In conclusion, the discovery of the KBC Void's influence on the Hubble tension is not just an astronomical curiosity, it is a watershed moment in the history of cosmology. It challenges the very foundations of how we measure the universe's expansion, urging us to reconsider our assumptions and open new pathways for exploration. As we continue to probe the mysteries of the cosmos, we will undoubtedly find that the vast empty spaces between galaxies are not just blank voids. They are the gateways to deeper understanding, pushing us to rethink everything we thought we knew about the universe and our place within it. The journey ahead promises to be as thrilling and transformative as the discoveries that have already reshaped our view of the cosmos. As exciting as the recent discoveries about the KBC Void are, they also come with a host of challenges that make it difficult to fully understand the scope and implications of this extraordinary phenomenon. While the void's influence on cosmic expansion and the Hubble tension offers a tantalizing glimpse into the deeper workings of the universe, it is not without its complexities. In fact, studying the KBC Void and its impact on the cosmos presents some of the most significant hurdles faced by modern cosmology. One of the primary challenges in studying the KBC Void is the vastness of the region itself. Spanning nearly 2 billion light-years, the void is an unimaginably large stretch of space, and its sheer emptiness makes it incredibly difficult to observe and gather data. Unlike other cosmic phenomena, such as galaxies, stars, and nebulae, voids don't emit light or other detectable signals. They are defined by what is not there, by the absence of matter and the faint traces of the gravitational influence they exert. This lack of observable matter makes voids nearly invisible to traditional observational techniques, leaving astronomers with limited ways to probe their properties and effects. The very nature of the KBC void creates significant observational challenges. While scientists have made great strides in measuring distant galaxies and supernovae, much of the data that could reveal the void's impact is difficult to collect. Standard methods of distance measurement rely on light from distant galaxies, but in the KBC void, the galaxies are far less numerous, and the light from those few that do exist is often dimmer and more diffuse than in denser regions of the universe. This makes it difficult to get accurate readings of galactic motion, redshifts, and expansion rates in the void. Furthermore, the void's influence on local gravitational fields complicates the picture even further. The gravitational effects of such a large, underdense region are subtle but profound. These effects can alter the way light travels through space, causing phenomena like gravitational lensing and the integrated Sachs-Wolf effect, which distorts our observations. Understanding how these local gravitational anomalies influence the broader universe requires sophisticated mathematical models and precise simulations, but the complexity of the calculations is a barrier in itself. For every new discovery, there are still countless unanswered questions about the void's true impact on the fabric of spacetime. This brings us to another significant challenge. The theoretical models that attempt to explain voids like the KBC void are still in their infancy. While recent research has revealed how such voids might accelerate cosmic expansion and influence local measurements, the models that describe the behavior of voids are still being developed. These models must account for a wide array of factors, everything from dark energy's role in shaping the expansion of space, to the gravitational influence of surrounding galaxy clusters, to the peculiarities of light and matter within the void itself. Theoretical cosmologists are working tirelessly to refine these models, but the complexity of void dynamics means that much more research is needed before they can fully explain how voids like the KBC void fit into the larger cosmic picture. In particular, one of the most pressing questions is how voids influence the large-scale structure of the universe. While we know that voids occupy most of the volume of the universe, how they interact with the filaments, walls, and clusters of galaxies that surround them is still not fully understood. What role do voids play in the formation of galaxy clusters, and how do they shape the way galaxies are distributed across the cosmos? Understanding this interaction is key to understanding how the universe evolved from its early, homogeneous state to the complex web of matter we see today. Moreover, there are still significant gaps in our understanding of the evolutionary history of voids. How do they form, and why do some become as large and deep as the KBC void? What drives their expansion over time? The prevailing theory suggests that voids are the result of gravitational instabilities in the early universe, where regions of slightly lower density began to attract less matter, growing larger and more empty over billions of years. But we still don't fully understand how these processes unfold. Do voids continue to grow indefinitely, or is there a point at which they stabilize? How do they interact with dark matter and dark energy over time? These are questions that require more data and more refined models to answer, and much of the research needed to answer them is still in the early stages. There is also the challenge of quantifying the void's influence on other cosmic phenomena. If the KBC void accelerates local expansion, does it have a corresponding effect on nearby galaxy clusters or the cosmic microwave background? How does the presence of such a large, empty region affect the distribution of dark matter and dark energy on large scales? These questions are deeply connected to our understanding of the universe's evolution and could ultimately lead to a more refined understanding of the forces that shape the cosmos. But answering them will require more than just theoretical work. It will also require deeper and more precise observations, something that is currently hindered by the void's vast emptiness. Despite these challenges, the implications of understanding the KBC void are immense. The discoveries made so far have already reshaped some aspects of cosmology, particularly in regard to the Hubble tension and the rate of cosmic expansion, but there is still so much more to learn. As new telescopes come online and as more sophisticated simulations are developed, we will likely gain a clearer picture of the void's true nature. The potential for breakthrough discoveries remains high, but to truly unlock the mysteries of the KBC void, we must continue to refine our techniques, enhance our models, and push the boundaries of what we know. In the coming years, astronomers will likely push the limits of current observational technology, using more advanced telescopes and space missions to peer even deeper into the universe. The James Webb Space Telescope, with its unprecedented sensitivity, will be particularly crucial in this regard. Its ability to observe distant galaxies and supernovae in unparalleled detail will allow scientists to gather more precise data helping them understand how voids influence the surrounding cosmic environment. In tandem with the development of more powerful computational models, these observations will help refine our understanding of how voids, like the KBC Void, fit into the larger structure of the universe. Ultimately, studying the KBC Void is not just about understanding an isolated region of space. It is about understanding how the universe works at its most fundamental level. The discoveries made in the coming years will likely reshape our models of cosmic expansion, the behavior of dark energy, and the evolution of the universe itself. But to get there, we will need to overcome the significant challenges posed by the void's vast emptiness and the complexities of gravitational anomalies. In the end, the KBC Void is a mystery, a vast cosmic riddle that remains unsolved. But as we continue to study it, we will not only uncover the secrets of this particular void, but also take a giant leap forward in our quest to understand the universe as a whole. The journey ahead is filled with challenges, but it is also filled with boundless potential for discovery. In the end, the discovery of the KBC Void challenges everything we thought we knew about the universe. For centuries, we've looked to the stars and galaxies as the building blocks of the cosmos, creating models and theories based on the assumption that the universe was, at its core, relatively uniform. But the KBC Void has proven that our perception of the cosmos is not as simple as it seems. This vast, underdense region of space, so massive it spans nearly 2 billion light-years, has disrupted the very foundation of cosmology. Its influence on the Hubble tension is just the beginning. The discrepancy between measurements of the universe's expansion rate, once thought to be a measurement error, may in fact be the result of our location within this extraordinary cosmic void. If confirmed, this discovery could force us to reimagine the laws that govern the universe's expansion, requiring us to rethink not just how we measure the cosmos, but how we understand it on the most fundamental level. As we continue to study the KBC Void and other voids scattered throughout the universe, we are confronted with profound questions. What do these empty spaces tell us about the universe's structure? How do they shape the formation of galaxies and the evolution of cosmic forces? And what other mysteries might lie hidden within the vast, seemingly empty stretches of space? These cosmic deserts, once seen as insignificant, may hold the key to some of the universe's most profound secrets. The KBC Void has opened a new chapter in our exploration of the cosmos, but this is only the beginning. The path ahead is filled with potential for discovery as scientists continue to refine their models, collect more data, and develop new theories to explain the void's role in the larger cosmic picture. There is still so much to learn, and the answers we uncover will undoubtedly reshape our understanding of the universe. In the face of these mysteries, one thing is certain. The universe is far stranger than we ever imagined. The KBC Void is just one of many cosmic anomalies that challenge our understanding, and as we continue to explore the great expanse of space, we will undoubtedly encounter many more. The vast emptiness of the cosmos is not just a void, it is a doorway to deeper understanding. So keep wondering, keep exploring. The universe has so much more to reveal, and with each discovery, we move closer to unlocking the true nature of the cosmos. The journey of exploration is endless, and with each new insight, we get one step closer to answering the deepest questions of existence. The KBC Void has ignited a curiosity that will propel us forward into an age of discovery, where the most profound mysteries of the universe are waiting to be uncovered.